Okay, take 3, somewhere in there. Let's see if we can get this rocking. We're going to talk about this. We're talking about rolling motion. This is the energy equation that governs it. To be clear, there are 2 terms that talk about rotational energy. There's the translational and the rotational. This is in contrast to swinging motion. Remember, with swinging motion, when you had a pendulum swinging, we did not have the 1/2 mv squared. So with swinging, we had an mgh and a 1/2 I omega squared. With rolling, we have both. All right. Okay. So as an example of non-conservative work for rolling motion, you could consider drag or something. Now, there's something I'm going to get to in a minute that's a very confusing aspect of rolling motion. Rolling motion is probably the most confusing type of motion, all right? So friction is required if you're going to have rolling motion. If you don't have rolling motion, it would just slide like an ice cube and it wouldn't ever twist. So without friction, you wouldn't have rolling motion. However, the point of contact of the wheel with the road is not actually moving relative to the road. Because of the friction, it twists, but that friction causes 0 displacement relative to the wheel, and therefore it does no work. So without friction, you wouldn't roll, but the work done by friction in rolling is 0. Digest that for a minute. Without friction, you don't roll, but friction does no work. So this term usually drops out. So in answer to Nick's question, we're probably not going to have any questions where there is work non-conservative there. You could have it if you included something like air resistance or something like that. All right. So we're going to ignore that. Okay. Yeah. All right. So now there's two types of motion. Rolling with slipping, that's like a bowling ball that's going down the alley and you see it kind of sliding, but also twisting a little bit. That is not going to be on your test 2 or the final exam. Rolling with slipping is not on the test. If you care and you want to learn more, that's problem 10.68. You can learn a lot from that problem, but 10.68 at the bottom of page 81 is not on the test. It's a common engineering question, to be honest. All right. So, yeah. Where's that chat box? I lost it. All right, I lost the chat, but okay. Now, rolling without slipping, that is the more common, that's just standard rolling motion. So unless otherwise specified, we're going to assume rolling without slipping. When that is true, we can use this result up here. Okay, that's this rolling motion. And usually this work term goes to 0. Furthermore, I want to stress this one special spot here. Yes, it's yeah. Okay, so in this case, I want to point out this right here and this right here in relation to this equation right here. If you use equation 1, you can get rid of one of these 2 variables. It looks like there are 2 parameters there, but for rolling motion without slipping, V and omega are pretty much interchangeable there. So I could take, for example, one common thing is if I want to find omega, I just replace this with r squared omega squared, or r omega quantity squared. And I think that's an initial. So that's right here. This thing, you can get rid of it and get it in terms of omega. Alternatively, if a question is asking about speed, you could take this and drop that out and make that v squared over r. And I think that's an initial there. So just be aware that these two terms are linked and these two terms are linked by this equation. That's a huge deal. It reduces, and yes, r squared too. Thank you. Yep. Okay, very good, very good. All right, good to know. And interestingly enough, because all these things are true, you could in theory use your rotational kinematics as well. So you can solve this problem with energy, and rotational kinematics also applies. The other thing that applies is translational kinematics. And if you want to, there are two ways to do it with torque. There's torque 1 and torque 2, and I'll address that in a minute, all right? So there are two different ways. So this problem can be attacked in many different ways. You could use energy and kinematics. You could use torque and kinematics. You could use kinematics and kinematics. You could use torque and torque, all kinds of different things, all right? So, whoops, let's clear that out. All right. Here's some other things. Static friction is present, but this is a common misconception. Usually when a ball is rolling, it's not on the verge of slipping. Only in very rare situations would this thing be on the verge of slipping, okay? So in general, just because you have friction doesn't mean you can use this. In fact, do not use that unless you are told otherwise. Like I said earlier, friction does no work if there's no slipping. We saw that friction does negative work when it is slipping, but in this case, it's rolling without slipping. That means the friction does no work. Let me see if I could scoot down just a little bit here. Oops. All right, and then, oh boy. All right, so bullet 7 is the crux here. So you can always use the center of mass as the axis of rotation and do a torque problem. And I'll explain why this is challenging in a minute. It turns out bullet 7, conceptually speaking, is much harder to understand, but much easier to compute. So we're going to use this trick, and I will show it to you in a minute. So if you're wondering what I'm talking about, don't worry. There's the point of contact with the road is not moving. That point is called the instantaneous pivot. So when this ball is rolling downhill, you can think of it actually as swinging downhill, and then the pivot point changes to the next point on the ball, and then it swings another little half a radian or something. Then the pivot point changes again, and it's literally just swinging about the point of contact with the road. What's weird is the pivot keeps moving from instant to instant, and that's why it's called the instantaneous pivot. At any one instant, the point in contact with the road can be thought of as a pivot point. And it's a super trippy thing, but it ends up working out. All right. So more on that in a second, but this is something that people forget all the time, this pink line right here, okay? If you use the instantaneous pivot, you do not use the center of mass moment of inertia. You use I parallel equals I center mass. And then for this particular class of problems, it's always m squared or mr squared, where r is the radius of the rolling object. Okay. All right. And this doesn't really make sense until we get into a problem. So we should probably get into a problem here. Whoops. So let's scroll down here. And then if you're curious, yo-yo problems are exactly the same. And maybe you heard of a rolling friction. We're going to ignore rolling friction. If you're curious, I do know I saw an old MCAT exam, and it was actually on the MCAT, rolling friction. So what they did is they wrote a little essay on it and asked you to interpret it. So rolling friction sometimes shows up. The best way I can describe rolling friction is, imagine you had a basketball or a tire, and as it rolled, the bottom part of the tire would squish a little bit. Well, it takes some energy to squish that tire, and then when it unsquishes, you've converted some of the kinetic energy into internal energy of the molecules from squishing them, right? If you just squeeze something back and forth a bunch of times, it's going to get hot. And so that's basically what that rolling friction is. If we use a bowling ball that's very rigid, or a metal hoop, or something that doesn't flex much, rolling friction is very negligible. Okay. Or if you're rolling on a carpet, you could imagine, well, then there's a lot of friction from squishing the carpet and unsquishing it when the ball rolls past. But we're going to roll on hard surfaces with hard objects. And so we're going to assume that rolling friction is negligible for our class. We just got to pick our battles here. All right. So we're going to go to 10.59. Looks like this is an outdated, this is outdated now. I need to fix that up. This should say 10.59. All right. So if we can get this one, you can get all of these. All right. So here we go. 10.59. You have two objects side by side on a ramp. You're going to release them from rest. Think to yourself, what factors might affect the race? All right. Take a second to take your own guess. And if you want, you could write it down on a scratch paper or something. But so for example, let's say we had a sphere and a cylinder, and we're going to roll that down there. Or what if we had two different spheres, right? So I'm just curious, which of these factors you think should affect it? Will the mass affect who wins the race? Will the radius affect who wins the race? Will the shape affect it? Will neither one? Will both? Will something else that I didn't mention do it? All right, so hopefully you have your intuition there. What we're going to do is we're going to start by doing this problem with energy. And then I think what we're going to do is come back at the end and show you about instantaneous pivot with the torque. So let's go with this. I'm going to do a conservation of energy problem now. Let's go take a look at it. All right. $10.59, I think, right? All right. So here's the equation. This is conservation of energy. Initially, it's up in the air some distance. And if it helps, let me draw this really quick. We're assuming the ramp has length L. We're assuming this angle is theta. So hopefully you agree with me that this side over here is L sine theta. That's just the height. Okay. And now if you want, if you're worried about the height of the object itself, hopefully you can see from this picture, if I go from right here to right here, that's the same as going from right here to right here. So we expect that the height really is L sine theta. Initially, you have all gravitational. There it is. At the end, it's now down to zero height. So at the end, this term drops out. There's no gravitational. I already explained what happens to the work done by friction. Even though there is friction present, the work done by that friction is zero. So notice here, this is the translational energy. This is the rotational energy. Everybody watch out for this one. There's this 1/2, and then there's I. And remember that a lot of times the I has a fraction in it as well. A lot of times people forget and just say the 1/2 out front and then forget the fraction for I. I has a fraction too. All right. Oops. All right. And so in this case, notice I replaced that I omega squared with I v squared over r squared. And at that point, you're like, oh, this isn't too bad. You group the two v terms and then isolate it. So take a second and make sure you agree you could do that. You multiply by 2, so you get a 2mgl, and then you factor out an m, and you factor out an I over r squared. And then I hope that problem makes sense. Here's the cool part about it. inside of I, whoops, inside this term right here, it's usually some factor times mr squared, right? Where k, for example, k is usually a number like 1/2 for a disk, or it's 2/5 for a sphere, something like that, okay? Or maybe it's 2/3 for a spherical shell. The point being, notice the m and the r are going to drop out. You've got a mass that drops out, and this radius squared drops out. And it turns out mass and radius don't matter. It's the shape. Isn't that crazy? In theory, if you had a bowling ball, a solid bowling ball that's uniform, bowling balls are a little bit tricky because inside there's non-uniform composition. But if you had like a basketball and a tennis ball are both spherical shells. They're both approximately the same thickness, maybe not quite, but yeah, so hopefully they would be finishing at approximately the same time. Or you could compare a thin ring and a disk. That's the classic physics demo. You roll it down and notice that a thin ring has the mass really far away. Remember, thin ring is just mr squared. Whereas a disk over here is a 1/2 mr squared. And so it turns out the smaller shape factor, the smaller this parameter k is, the smaller the fraction sitting in front, the faster you get down. The faster you get down means you must be moving faster. So this one's moving slightly faster, 15% faster than that one. And I'm going to pause and get to the chat. Okay. Not size. It's not size. So yeah. Yes. Isn't that, it's amazing. It's the shape that matters. All right, let's get back to it. All right, and so now I want to show you the question again. Okay, so we kind of, this is fun. You can see which object should win a race. So 2 spheres should tie, 2 disks should tie, 2 spherical shells should tie. And then in general, a sphere has mass closest to the axis. That will be the fastest, followed by a disk, followed by the spherical shell, and then finally the thin ring. Okay, let me check that chat. Yep. That's right. So hollow versus solid matters. Sphere versus spherical shell, I don't consider those things the same shape, I guess. But yeah, so I was assuming that a spherical shell is not the same shape as a sphere, but I could see how you would think that. That wasn't my intention to confuse you like that. Sorry about that. All right. Okay, and now this is the other part that we really want to get good at. Angular acceleration. All right. So in this case, I want to clarify something. Remember, you have an exam Monday. You're reading an exam question. When you see angular acceleration, you should be thinking either torque or kinematics. And that's the kind of thing that you can use. For swinging motion, can't use kinematics, so you would go straight to torque. So in general, when I see a question asking about angular acceleration, that makes me think about torque. All right. Now, when I saw this question here, it says, oh, it said do an energy problem, and it talks about velocity. So if I see velocity or omega, a lot of times I'll try and do energy. If I see angular acceleration, I'll try and do torque. Let's go look at the free body diagrams for 1059 in the solutions. All right, so here's the answer. And then here are 3 styles of solving this problem. So I think it's worth seeing all 3. Style 1 is my go-to. I like style 1, but it requires you to learn a little bit and think a little bit differently than maybe what you've done in the past. Okay, so here's the deal. This point is called the instantaneous pivot. That is the point of the wheel or the ball or whatever that is in contact with the road. So that's, I'm calling it the instantaneous pivot, all right? Now, in this case, look at this cool thing. The green forces here, friction and normal force will not cause a torque about the instantaneous pivot. Okay, the line of action for friction runs right through the pivot. The normal force, the line of action, runs right through the pivot. The only thing that doesn't is mg. So let me clear out these drawings. If this is my pivot here, this green dot, mg has a line of action like this. All right, so there's the line of action for mg. So you could try and figure out this distance here, which is r perpendicular, right? The lever arm. Or you could just, if you don't want to figure that out, you could say, well, I know this distance right here. This distance is r. And then because of some, let me just do this really quick. I know the angle here is theta. So if I have a ball sitting here and I draw this mg, right? This angle is also theta, because this angle right here is 90 minus theta, if I could draw it any at all. How do I know that? Because this was supposed to be a right angle. So this angle, the whole point of that was to say that that angle inside of there is theta. So you could also just say, well, the torque is, here's the force, here's the distance times sine of the angle. Or you could say this is the lever arm, r perpendicular. All right. So that's this line. And then from there, it's a piece of cake. Oh, this moment of inertia is not at the center. Take a look. The distance between these two axes is r. So my moment of inertia is the moment of inertia at the center plus mass times the distance squared. Distance in this case between the axes is r. So from here, you got this, you know this is going to be whatever shape you've got. So if you were doing a disk, you would say that's just 1/2 mr squared, and you'd be off to the races. Okay. That one is actually really easy to do. But it takes this, you have to accept that the instantaneous pivot actually makes sense. So I'm going to check the chat really quick. Sphere. The sphere wins. Solid sphere. A solid sphere has, remember, in general, moment of inertia always has, moment of inertia is large if you have mass far from the axis. Moment of inertia is small if you have mass near the axis. So in all of these problems, and my apologies if Jay already got our question answered, but I'm going to go back and answer it. Look at these. There's a moment of inertia in the basement. The one with the smallest moment of inertia should win, right? Because the fastest one means it got down the hill fastest. So whichever one has the smallest moment of inertia will get down the hill fastest. Think of it another way. How about this? Objects with large moment of inertia, it's hard to change their rotational state. So the bigger your moment of inertia, the slower you are to get off the line, the slower you are to start moving, right? Because if you have a big moment of inertia, it's hard for you to start rolling. So something with a small moment of inertia, like a sphere, should race down and get down there fastest. And that's why the sphere, which has the smallest shape factor, actually gets down fastest. All right. Any questions about this instantaneous pivot? Any questions about that? As long as you're willing to accept this, it's actually really easy to do these problems. The nice part about the instantaneous pivot is I don't need to know what the frictional force is, so I can't accidentally screw up and assume it's on the verge of slipping and plug in the wrong equation. This is one of the benefits of this method. The drawback is you have to remember to do that step. You have to remember to use the parallel axis theorem. All right, style 2. If you use the center of mass as the pivot, now think about this. This is also valid. We get two choices for this one rolling problem. In this case, mg, line of action, mg causes no torque. Normal force causes no torque. So in this case, friction causes the torque. And now this, it's rotating about the center mass. That is I center mass. And let me catch up with the chat question here. The instantaneous pivot is a mathematical trick which makes computations much faster, in my opinion. More on that in a second, Ryan. I'm going to kind of ignore your question for a minute. All right. So, all right. Think of it as a pure math trick. That's what I want you to think for right now. Okay, here, this works great, but the problem is I don't know what friction is, right? And in fact, friction is not mu static times the normal force. This equation is only true if it's on the verge of slipping, but this is rolling, not on the verge of slipping. So it's like, well, that's just not going to be true for most problems. So what do you have to do? Here's the force equations. I think you could agree with this one. There's an mg, which has a component this way and a component this way. There's friction this way. There's normal force. That's a pretty bad drawing. That's a little better. All right. And so you could see that mg sine theta, this term right here, is this part right here, minus friction equals ma. All right. And then, so once you do that, you could plug in all of this, which is fine. But wait a minute, A and alpha are linked. They are connected. They are constrained together by the radius. So then you could plug in this, and then you start doing a bunch of algebra from that point. I hope you agree style 2 takes a little bit more effort. I will say that style 2 is always correct, even when it rolls with slipping. So style 2 is a good style to know if you go on in lecture. I do see there's some chat activity. I'll get there in just a second. And then I'm going to do this last one really quick. This is another cool way to do rolling motion. If you do the energy problem, you can do energy and then just slap in some kinematics and get it that way. So either style 1 or style 3 seem to be the way to go. And again, style 2 is totally valid. I'm going to stop for a second and check all those chats. So, okay. Okay. Yes, I agree with that statement. Okay, cool. Yep. Yeah, exactly. Okay, cool. I think you got it. All right. And then I'm going to show some stuff on the next page. If you are serious, if you're a mechanical engineer, you got to know this stuff. So if you're a mechanical engineer, you really want to know this stuff. And this is my way, this is kind of my summary. Part of the reason this is so tricky, it can be viewed as all kinds of different ways. And depending which website you look at on the internet, you're going to see all of these different ways. Here is the first way that we talked about, summarizing. You have translational motion and rotational motion. And now when you add those up, look what happens. Let me get my purple out, right? This plus this equals at rest. This thing is translating forwards, rotating backwards at the bottom, and that's what causes it to be at rest at the bottom by a fluke. Notice the middle part, there's no velocity, so this plus nothing gives me just the center of mass moves to the right. So you can actually treat the center of mass like it's translating kinematics because it's not rotating. That's why we're able to do that. And then at the top, you have it's moving to the right, plus it's rotating to the right, which it's actually going twice as fast up top. If you wanted to, you can view that as this green picture down here. Look at this. View it as rotating about this spot that I'm trying to draw in bright green. If it's rotating about there, right? This point would be swinging this way. This point will be swinging this way. Now, I should be careful. This only shows the X component, and so it's not a full picture, but it does make sense if you think about it as this point is now going to start accelerating upwards, and it's going to force these weird shapes like this. But I don't know. Let me get out of this as quickly as possible and see what we can. All right. Yeah, so you can view it basically either you have a choice. You can view it as, let me get, you can view it as this up here, or you can view it as these two. Either way. And that's just cool, and that's a weird trick. If you view it as this way, that's the mathematical trick that we're doing. You're choosing to either view the center of mass as the rotation axis, or you're choosing to make the instantaneous pivot the rotation axis. And then once you make that decision, you do have to choose your math correctly based on that. There's some other comments here. That's pretty much it. So let me see if I can stop the share there. All right. Let me catch up on this. Okay. All right. What do you think? Is everybody doing all right with that one? That's a heavy duty problem. Heavy duty problem. I think the thing to do now would be for us as a group to try and attack 10.60. Now, I do want to say right off the bat that rolling motion and yo-yo unraveling motion are the same thing. You can think of the yo-yo as rolling down the string, okay? So that's why these two problems are coupled together. I think rather than me just blathering and telling it to you, this would be a good time to try and do it yourself. And I'll give you a second to get started. So let's look at 10.60, all right? And I'll bring it up. Okay. This just does not come easily, so I want to make sure I pause long enough to give you a chance to come up with some questions. Okay. And I think the best thing we can do, let's start here. Looking at question A, what do you think? Is it in free fall or not? Hopefully you thought no, or not free fall. There's a string pulling up on it. Free fall means only one force acting, and it's gravity. Here, there's going to be a tension up, and there's going to be weight down, right? So this is clearly not free fall. I would expect it to be less than G because there's a tension pulling upwards on it. Hopefully that was intuitive to you. If so, awesome. If not, well, that's cool. And then I want you to, instead of doing these problems, look at these really quick. Part B asks about rotational speed. Think, what type of problem should you do? If that was the test question, hopefully you'd say energy. Try energy first. Okay, energy. Why? Because it says speed. Speed problems usually can be solved with energy. Not always, but you might think kinematics. You could also use torque plus kinematics. That would also solve it, it turns out. All right, but energy is usually the fastest. And before we do that problem, look at this one, translational acceleration. Because we already did energy here, we already did energy in this previous part, the fastest way would probably be kinematics. Because we're going to know the final speed. If we know the speed, it might be easier. But notice there's translational and rotational, so we're going to have to do some conversions with the radius. You could just skip all that crap and just go straight to torque using the instantaneous pivot. And that's what I would probably do. All right. The nice thing about doing that is that if you do this one wrong, it doesn't screw up this one, right? So on test day, I would probably do energy for this one, then torque for that one. And then if you want, you could check, and you should get the same result if you use kinematics. All right, hopefully I didn't go too fast there. That's what I want you to know right now, what technique to do. So I'm going to check the chat really quick. I think it's good to know both. No, I didn't just tell you there's a yo-yo problem on the test, but I'll tell you this: there's definitely something from these upper problems in chapter 10 on both the test and the final. So you're going to get some kind of problems like these nasty ones we've been doing on both the test and the final, just because they really force you to know everything. So expect, I mean, this is a great problem to practice. I'll put it that way. All right. And when you see these, you also need to identify what technique right away. Because Jay's question is, which is better? My answer is know them all, because for different problems, different techniques are much faster. If you see a problem that says acceleration on the test, and you only know energy and kinematics, that question will then take you twice as long as everybody that knows the other technique. If you don't know energy, you're toast as well, because what if I ask you a speed question? Then you have to go through all the work of the torque problem and kinematics, just so you got to know both. So no torque, rotational and trans kinematics, and energy. No okay. Oh yeah. Oh yeah. The exam is all its own thing. Yeah. So yeah, every year I make up all new questions. I've managed to not they're very similar to the ones you have, right? If there's a hole, I move the hole to a different spot or something, right? But it's all the same crap. Or maybe I did a problem in here with a certain shape and then I'll change the shape. So yeah, it's not like they're dramatic variations. And by doing all the problems that you've done in the homework, you've done all the stuff that's on the test. But yeah, I'll just mix it up by changing what the old problems were and just, I don't know, maybe I'll change a pivot point, which changes a lot of crap, right? It's the same procedure, find the center of mass, do this, do that, etc. But if you have a different coordinate system or a different pivot point, it's just like, oh man, I got to start over. And if you've been doing the problems, it's very formulaic. It's, yeah. Sean, generally speaking, not. It is possible. We saw one case earlier, a Ferris wheel. If you had a swinging motion, if you have something pivoted at the center, then alpha could be constant. But if you have a pendulum that the pivot is at one end, then no. Is that good, Sean? Yeah. So generally for swinging motion, alpha is not constant. It's rare to have anything be never in physics, as you know. All right, so I'm going to go ahead and look at the solution to this one right now while we've got it. Oh, what a great solution. This must be one of those ones that I do in lab too, I think. So yeah. So maybe we could, this will be a good question for you to see if you can figure this one out. So see if you can write down the energy equation, and I will too. And notice here, it looks like I means I center mass. Okay. So I'm going to give myself a little space to work here. Okay. So that's supposed to be my yo-yo. All right. And so if I draw this one, there's a tension upwards right here. There's the tension acting on this one. And then here's mg downwards. And I think mg's got to be bigger because it's winning. And so that's going to be useful if you're doing part C. If I'm doing the energy picture, I guess what I could do is I could say, here it is right here. Versus here. All right. And so in this case, if I'm doing the energy picture, I need a height, right? So there's some distance it falls. It looks like that was h. So if it falls distance h, at the initially, I think it was not rotating. So omega equals 0. At the end, this thing is rotating. So I think it's rotating this way as it rolls down the string. It's also translating, right? Because it's rolling and it's translating. So that's the energy picture that I'm thinking of, if this helps. From there, you should get something like mgh is the initial energy. There's no, oh, and to be clear, I guess, V is also equal to 0. It's not translating, it's released from rest. I hope it said that in the problem. Yes, it says release from rest. There's no slipping. So the work done by friction equals 0 because problem said no slipping. So that's what the no slipping is for. It's to tell you that. All right. All right. So mgh is the only energy at the beginning. That lets me go back into here. And then at the end, I'm going to have a 1/2 mv squared. That's for the translational motion. And then I have to remember to add in 1/2 I omega squared. This is another one of those problems that I always do in lecture. And so that's why the solution is so sparse. And then at this point, hopefully you're thinking to yourself, ding, 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 ding. I'm looking for omega. If I'm looking for omega, which one of these two terms up here should I swap out? Probably this one. That is, let's see, I know that V equals R omega. It's not your omega, it's R omega. So that means V squared is R squared omega squared. So that means, oh, so that allows me to pop that in right there. And then I factor this out, and that's where you get this result. Hopefully that made sense. I'm going to pause for just a second and check the chat here. Hopefully that made some sense, even though it's crappy writing. Go for it. Question. Just speak up loud if you want.
Oh yeah, this is a lot quicker. Okay, so I'm wondering, when we do the I, is that going to be the combination of that cylinder plus the two ends of the yo-yo, essentially?
Good. Yes, very good. So to be clear here, I would be I total would equal I of the cylinder plus, I think there's two plates,
Two plates,
I
yeah.
of the squares or something, right? Is that good?
Last question.
Yep.
It is the I, but technically the cylinder is off center. No, it's not. No, everything is on center. So it should just be
Right.
the center of them. Right.
It's
Okay.
very weird. You're thinking
Yeah.
about it as, remember, you could think about it as rotating about here. It's rotating about the center there, but it's rolling on this road, but it's not a road, it's a string. So you could think of the string as the road, and again, it's very
Right.
similar. The center of mass is not touching the road, but it still can be, we can still use that as the rotation axis.
Gotcha. Okay, thank you.
Yeah, cool, cool. All right. Any other questions on that one? I'm going to try and do the torque problem now as well. And I need to, I think I need to clear out this a little bit. So let me get my eraser here. So I have some room. All right. And now I got to be careful here. I better write something right now. This is I center of mass. All right. So that's, I'm assuming that would be the cylinder about the center of mass and the square about the center of mass. All right. So now when I look at the torque problem, you could choose whichever pivot point you want. But to me, since I don't know the tension and I do know mg, this seems like a no-brainer. Take a look. I get this right angle here. This distance is r. The distance between the pivot point and there's r. So I could do a torque problem and just say r mg equals I alpha. Now be careful here. It's very close to this one. This is not quite it. I need I from the parallel axis theorem. So nothing comes for free. But I've done the parallel axis theorem. Whoops. Equals I, let me, this is what's cool about this. If you know the total mass of the squares and the axle, and you already did all this work to figure out the moment of inertia at the center, all you need to do is just take that same thing, shove in the total mass times the distance you shift it, and you get that. So that's what you need to shove in right there. All of this gets plugged in right there. And once you do that, I hope you see this mr squared in the equation right there. In case you're wondering where that comes from, this 1 plus, it's basically from this parallel axis piece. And if you're wondering, wait, why isn't there a sine theta? Hopefully you see that there's this right angle here. So the torque about the instantaneous pivot is this. And again, sine of 90 equals 1. If you're wondering, why isn't there a sine theta? There is a sine theta, it's just 1. All right. Let me pause for a second and see if I missed anything over here. No, looks good. All right. I'm going to clear out these drawings really quick. Remember, there is the live share, whatever live stream. So we can always go back if you need to see this again. And then, yeah, this is sort of what we were just talking about with Nick. You got to remember to add in the 2 plates or something like that. All right, so if you're wondering where the 1/6 comes from, it's because it's 1/12, and then I think you get 2 times that, something like that. All right, and I'm going to jump back over to here. Let me get back to the question, see if there's anything I missed. All right, so if you're wondering, the rest of this stuff was just for lab, but we're doing coding instead, so you can probably flake out on the rest of that stuff. But if you want, you can you could take your own yo-yo, do the masses, and see if physics works out if you want to do a lab at home. All right, that's for fun. All right. What do you think? Doing all right? This seems like a logical spot to take a short break. And
I do
then
have
we'll
a
come
quick
back.
question if we could.
Go for it. Yeah.
Okay, so on let's see, what page was that? One of the pages where you show the center of masses, it's like a list, page 59.
Oh, you mean
The moment of
inertia?
inertias, yeah.
Yeah.
Some of them say like a thin plate. What signifies a thin plate? Like, how small does it have to be?
You know, it turns out it would be, let's see. Boy, I'd have to think a little bit there, but really you could do a quick calculation, and probably the easiest thing to do would be do a not thick plate. And then if you're going to do that, you would have to use the techniques shown. Probably you would probably want to use the tricks on page 67 and 68 show you how to get 3D shapes. And then I guess what you would do is you would just make the plate thinner and thinner until the correction from it being 3D was less than 1%.
I see what you're saying. So
And
as far as we're concerned, though, unless you specify that it's not a thin plate, then we use a thin plate. Okay.
I'm not giving you any thick plates. No,
okay.
no.
All right.
Yeah.
Okay.
Good question. Always good to wonder what is that constraint. And so you can kind of get an inkling for how horrible that might be if you looked at like 10.35 at the bottom of page 68, or it shows you how to get a cube. And it's like, oh my gosh. Ugh. It's just, yeah, there's just other techniques that you use when you get to that level.
Okay.
So thin plates for us. Good.
Sounds good. Thank you.
Yep. Other questions? All right. So I'm going to take a quick break here, and I'll come back and we'll do some questions from the last few problems in the section, like 10.61 through page 82. So pages 79 through 82 we'll look at then. All right. I'll stop the live stream.